problems using KC. And I kind of not really told you, what's the point of the C in there? Because we're going to see a lot of different Ks. We're going to see KP, we're going to see KC, KSP, KA, and KB. So a lot of different things next to it. The KC is the most generic one because it uses the concentrations. And that's the one we use a lot of times. But KP, obviously, is going to use partial pressures. And that's what I got to talk about today. And it's tough because I'm going to derive KP. Okay? First of all, let me tell you why I would want to use KP. A lot of times we have all gases. This is Roman numeral 5, by the way. A lot of times we have all gases as reactants and products. And in that case, it's actually sometimes easier to use pressures, more convenient to use pressures than it is to use concentrations. We can measure them easier, and so we'll use pressures. Well, how do we solve for KP? Well, there must be some relationship between pressure and concentration. And that's what I'm going to have to derive from beginning to end on this board. And it's going to start out okay with some simple algebra, but it's going to get a little hairy towards the end. So you got to follow with me here. It's not something, the derivation itself, you're probably going to be asked to do on the AP exam. But it does show you that you understand. I wanted to go through this because it's a great opportunity to review with you the ideal gas law, which is what we'll be using to do that. And we did that in Chem 1. But we haven't used it a whole heck of a lot. And the thing is, the ideal gas law pops up everywhere. It just shows up in all these different places. And I'll try to remind you of some of the places we've already seen it, and then I'm going to show you what we're going to use it for in this chapter. Okay, so let's derive Kp, which is equilibrium constant using partial pressures. When I say partial pressures, it just means the pressure of the individual gas in the container. It's not the total pressure in the container, but the pressure of that gas in the container. All right? All right. So, I said there has to be a relationship. Don't copy this down. I'm going to have all the stuff that's going to pop up on the board pretty much, except for one little thing. But there must be some relationship, all right, between Kc and Kp, and that's what I'm going to try to get to eventually. If I use, again, don't write this. If I use this equation, which I used to derive Kc back, a few weeks ago. We all know, and we've all been doing for 2 weeks, products over reactants, right? Okay, we've been doing that for 2 weeks. Now, so the coefficients, that's these guys here, the little a, little b, little c, they're the coefficients. We raise them to the coefficients, products over reactants. Here's the difference. What are these values in here? Why are there brackets around those values? What are they? They're concentrations in moles per liter. Molar concentration. We've been doing that quite a while. Is there a way I can find out what the molar concentration is, how it's related to the pressure? And yes, there is. Let me show you. That is called, that's going to use the ideal gas law. P equals nRT. Remember that one? Yeah, we use that a lot in Chem 1. And before I start this derivation, let me remind you of some of the places you would see the ideal gas law used on the AP exam and where we use it in Chem 1. Okay? You could use it very simply. Say I gave you pressure, volume, and moles, and I asked just for temperature. Or if it's solving, just literally solving for one of the variables. Okay? That would be one way. There's another place we used it for in Chem 1. We were able to use it in stoichiometry problems. When one of our calculations, one of our either reactants or products was a gas, I was able to predict, grams to moles, moles to moles, moles to liters. And I could do that even if it wasn't an STP using the ideal gas law. So we use it for that. We also use it for molar mass. If I could measure about a gas, the pressure, the volume, and the temperature, I knew I could pretty much figure out the mole, and I knew how many moles or how many grams I had to convert it to moles. I could figure out the molar mass. We did that. So those are 3 ways we used it in the past, and probably somewhere over the course of the review for the AP exam sometime in a couple of months, I will give you a few practice problems of those type as well. But the thing is, this guy pops his head up everywhere. Turns out that the relationship of pressure, volume, moles, and temperature, I can use in equilibrium problems as well. And that's what I'm going to show you how to do. Remember what I'm trying to get to. I'm trying to get to a concentration. Are there 2 values in there that are molarity? Put them together. Sure, there's moles and there's liters. So let's put moles per liter. Wouldn't N over V be molarity? Right? Everybody agree? But I'm getting ahead of myself. Well, first of all, let's do this. I want to get to the pressure. I want to be able to use the pressures, right? I'm getting a little ahead of myself. Pressure is going to equal nRT over V, just by simple algebra. Everybody agree with that? Simple algebra tells me P equals nRT over V. But here's where I was getting ahead of myself. What is N over V? That's molarity, right? It's just moles per liter, correct? If you're talking about a gas, obviously, you have to be talking about a gas. So N over V, if I bring that, by itself, what would I do with the RT? What would it be? Yeah. Well, N over T, first of all, is molarity. So basically, I want to still solve it for P. Again, I'm getting ahead of myself. So N over V is molarity. I substitute in capital M for N over V, and that's what I get for the pressure. Does that make sense?
Oh.
Yeah, I was saying the opposite. I was saying I was solving for molarity, but I meant...
You're just substituting...
Exactly. M for N over V. You see that?
Yeah.
So I told you this all starts out pretty basic algebra here, substituting in some different terms. We know N over V is molarity. There's N over V in the equation, so pressure is going to equal molarity times RT. That's nice. All right. So, now, again, I'm getting ahead of myself. Before I was trying to get to this. What will molarity then be? Molarity will equal, we'll have to do to both sides. Yeah, I'll have to divide both sides by RT, so I'll get P over RT. So, y'all good with that? Again, that is not the hard part. That's the easy part. I think most everybody else could figure that out. But, would you have? Probably not. Obviously you wouldn't have thought of that. I never did this. I never did really KP when I was teaching this in the past because I've always figured KC, KSP, KA, they're all, enough. Well, now I realize there are going to be KP problems on the test, guaranteed. So I'm going to have to show you how to do this. So wherever there was a molarity in this equation, right? That's why I write this equation down now. You want to just keep going straight down if you can. I put it over here so I can fit it all on one board. Wherever you had a molarity, what could I now put in there? Pressure over RT. So it gets really ugly. Okay? And the reason we can do that, look here. D, C, D, A, and B, anything in brackets is a molarity. Okay? They're molarities. So I'm going to substitute in my molarity from here, P over RT, into here. If I substitute P over RT for every one of those, here's what it would look like. So wait till it all pops up, and then you can copy it down. Ready? Because it's going to pop up in different stages here. That will be your numerator, right? Now let me explain before you start copying. Why does it say PC, PD? Because it's the pressure of C over RT, pressure of D over RT, pressure of A, pressure of B over RT. It looks ugly. I told you things are going to get hairy, and we're not even at the worst part yet. Up till now, it's really been some relatively basic algebra. Substituting in terms, rearranging them so they can find terms that we actually want to use, and substitute it into an equation we already know. And then, we come up with this thing. Well, that's pretty ugly. It's not making my life any easier to do that, right? If I had to do that every time, it would be a pain in the neck. There's got to be a way to simplify this, and of course there is. And that's going to be the, an ugly part here. It's going to make it a little bit uglier, as you'll see. You watching?
No.
Now, at this point, it became too much to even fit in the space provided, so I'm going to write this part in. Okay. Here, can anybody see what's common to all these guys is the RT, right? 1 over RT. So I'm going to factor him out. I'm going to factor out the 1 over RT. So here's what it would look like. Again, give me a second to write it down and then make sure it makes sense to you. And believe me, it's not going to stay this way. It'll get easier. Yeah. I factored out 1 over RT from the numerator and 1 over RT from the denominator. Got it? Okay? And of course, what happens when you're multiplying? You might say, why is it C plus D over there? What happens when you multiply the exponent c times the exponent d? You're actually adding the exponents, right? Okay, that's why it looks like that. But that is, again, it's still awfully ugly. I don't like that. I've got to find a better way to put that in there. Better equation than that. But once you copy that down, I want to just get this next step, show you why it works based on that. Okay. Well, first off, this whole thing, I'm going to substitute in one thing. Don't write it yet because it's going to pop up here in a second anyway. Oops, sorry. Instead of writing P, C, PB over PA, P raised to, that's just going to be KP. So that makes it a lot easier. KP is just the products raised to the coefficients over the reactants. Now, what am I going to do with this guy over here? That is the ugly part. You might wonder where it came from. See if you can figure it out. I'm going to just have it show up here and see if you can figure it out. Why that is the nice, easy equation you end up getting from that. Let me erase some of this so you have room to see it. Okay. Looks like I've got, yeah. I'm going to have to erase this part over here because you can't see it. I made it a little bit too big here. I'll rewrite it a little smaller while you're copying that down. What's that?
I didn't get that.
You didn't get what?
That last part.
I'm writing it again in a second.
Don't add.
There, it's a little smaller now. It doesn't. Now, yeah, negative delta n. Okay, all of this where delta n changes, it means the product, the number of the coefficients up here, products minus reactants. Okay. Now, those of you who are good at math, can you see why that is the same thing as that? Does that make sense? Let me show you if you can. All right. Well, first of all, why is that negative here for RT?
Because the RT is fraction.
Yes, exactly, because it's always 1 over RT, 1 over RT. So a negative exponent means it's a reciprocal. Okay. Why is it delta n? Well, the delta n is the number of moles of the actual, it's the coefficients. It's these coefficients, AA plus BB. So let's take a look at it. So that would be like 2A plus B yields 3C, for example. What you would have is you'd have this guy up here, he would be a 3 up here, because that's all the products added together. This would be a 3 down here, because a 2 and a 1. Those are your coefficients. And because it's products over reactants, what do you do when you divide? You subtract. That's why it's delta n, products minus reactants. When they are exponents, you subtract. So believe it or not, this whole big, ugly monster can be summarized into that nice, simple equation. You say, well, why would I want to do this anyway? Believe me, I'm going somewhere with this, and just trust me, but I'm still not quite there. What did I tell you I was going to derive? I told you I was going to derive KP. What have I actually got? KC. Can you? There's one last step to do now. What do I got to do to the KP? Divide both sides by RT to the negative delta n, which would simply be RT to the positive, because when you divide by a negative, and negative is going to be a positive, it's going to be that. That's what the actual equation is. That's your final equation. And that is the equation that shows up right on your sheet for the AP exam. You're going to get this sheet. Actually, I'm going to give it to you today. 2 sides. And one of the things you're going to be doing, one of the you're going to be using, under equilibrium, it's going to say right there, KP equals KC RT delta n. Now, you would have no idea what that was if I wasn't going over this at this point. That's why I had to do this. And by the way, just write that down here. Delta n is the number of moles of products minus the number of moles of reactants. It's basically the coefficients. How many moles of products minus the moles of reactants. Now, I've done a ton of work just to show you how to basically derive this. The amazing thing about this is, after having done all this crap, can anybody look at that problem and see something about what delta n could be that would make this equation incredibly simple? Exactly. If delta n were 0, in other words, if the number of moles of reactants were equal to the number of moles of products, number of moles on both sides are the same, you could forget all about this guy. Kp equals Kc. It's the exact same number. Is that crazy or what? So write that down over here. Kc equals Kp, where equal number of moles of gases are both sides of the equation. Wow. Well, that's fun. And as much fun as that was, we're going to now apply it to an actual problem. Actually, we're going to apply it to two. We're going to solve the same problem two different ways. I won't have time, I don't think, today to solve them both ways, but we'll see how much time we have. I'm definitely going to solve it one of the ways when I give you the example. How about that? Now, you should be impressed at that. That's the longest derivation we've seen in chemistry, for sure. We're going to get another. We're going to derive the Henderson-Hasselbalch equation. We're going to derive Ka and Kw. We're going to derive a couple of other ones, but that one's pretty impressive, I think.
Do you have floss?
I do not. Okay. Copy this guy down. This is my one and only example, but we're going to solve it two different ways. Once you copy it, I want you to realize something about this guy. He is a problem that you could have easily solved if one letter was different. Instead of saying Kp, it said what?
KC.
Yeah. If it just said Kc, you would have no problem solving this. What's that? Are placed. Yes, there should be a D there. Placed. Thanks for noticing.
Yeah, temperature does matter.
Yeah, exactly. In this case, a lot of times up till now, we've kind of been ignoring temperature because for Kc problems, most of them just assumed you were staying at the same temperature for the equation, and I didn't really care. As long as the temperature didn't change, Kc didn't change. Now, if we're doing pressures, it's actually going to matter what the temperature is. Here's another thing that I often leave out of my problems. What letter you think should go after each one of those guys? What letter should be here for the state of matter? Yeah, they're all gases. They have to be all gases, or this doesn't work.
What's units of Kp?
Well, it depends. It depends because you can have different numbers of moles on different sides. You get different answers for the atmospheres. Most of the time, when you write K, you generally don't want to do this next. Okay. All right. Now that we got that copied, basically we're going to skip again 4 lines for the ice again, right? Okay. But before I do that, let me just say what I would have done had this problem been Kc. Does everybody see what would have happened if this were Kc? And I gave you that concentration. You would have divided that by the size of the container. You would have plugged it in here. Minus x, plus x, 0 for these guys up here. And then you would have solved Kc equals and solved for x. You would have used the quadratic formula, and you would have gotten your answer, plugged it back in. Right. Because he says Kp, we have a problem. I'm going to solve this two ways. The first way I'm going to solve it is using Kp. Okay? I'm going to solve it with Kp.
So we skip our 4 lines.
Skip your 4 lines, yep. And solve this guy using Kp. All right? Well, to use Kp, it's products over reactants raised to their coefficients, but we don't use concentrations. We use what? Pressures. Is there a way to convert the information given in this problem into a pressure? Yes. PV equals nRT. PV equals nRT. Before we start doing the problem, pressure is what I'm looking for, correct? Do I know the volume of the container? 5 liters. How many moles? Right there. R, constant. By the way, that constant is also on the sheet you're going to get today. Temperature, right there. I know what the pressure is just by solving it. P equals NRT. RP over P. I have all these worked out, so don't worry about getting your calculator out, because I knew we wouldn't have a lot of time. What's that? You good?
Remember what R is.
Oh, that's okay. Again, do you remember? Anybody remember R? 0.0821 liter atmospheres per mole Kelvin. Very good. And if you didn't remember it, it's on here anyway, along with all the other constants. Okay, how many moles do I have? 0.0334 moles. R 0.0821 liter atmospheres per mole Kelvin.
Isn't it in Kelvin? 448 or
Well, I'm not there yet. Temperature 448 Celsius. Good, Emily remembered. When you use the ideal gas law, volume's got to be in liters. Temperature's got to be in Kelvin, which is 721. All right, and over volume, which is in liters, 5.00 liters. Math, you do all that, you get 0.396 atmospheres. All right. Well, now we treat this problem as if it was the ice problem we thought it was, if that was KC. I, C, E, told you to leave that room blank up there. Your initial is 0.396 atmospheres. What's your initial pressure of SbCl3 and Cl2 if you don't have any of it? 0 and 0. Remember, this all works because pressures are directly related to the moles, you know, because there it is, that box up there. What does that box hold? 1 mole of any gas at STP, right? 22.4 liters, right? Okay. Oh, over the last couple of days, we've been doing Le Chatelier's principle. We've been having minus X and plus, and I've been thinking about that. Do I really have to think about this one? Where does the minus have to be? Has to be over here. Can it possibly be over here? No. So plus X and plus X. There are no other coefficients, so it's just plus 1X. So 0.396 minus X, X, and X.
Why did you say that?
Why is it minus X on this side, Olivia, and not on that side? What would happen if I had a minus X here? What would I get for an answer, whatever that number would be? Can I get a negative concentration? Yeah. You see, here's the other reason the answer, besides the math reason of negatives, here's the other reason. I put him into the container, and there's none of this. It only has one way it can go. It can only go that way. All right, that's how you know it's got to be a... What? Yeah, exactly. And of course, if you're in Gunther's class, if you're in math class, if you're in pure math, you can do that kind of nonsense. But you can't in reality. In reality, you know, that's why we get 2 roots for our answer. One of them, the negative root never makes sense because it means it's doing the opposite of what you said it was going to do. Okay, we've got all of our stuff here. We're going to plug in KC. KP. KP is going to be, and you must show me, at least for me, I don't, actually, the fact is, if this is a free response question in the test, you should show all this work as well. Absolutely. Important to show the work. SbCl3 times Cl2 over SbCl5. So Kp is 1.48 equals 0.3, equals X times X over 0.396 minus X. Okay.
1.48.
I think X times X. That's just a parenthesis there. I have it worked out. I got X squared. When you do what are you going to do here? X times X is X squared, cross multiply, distribute that across him, here's what you get. X squared plus 1.48X minus, can't read my own writing, 0.586 equals 0.
When you do the...
Right, then you grab your calculator, you plug in the quadratic formula, and you guys, listen, I have a feeling on the test, the AP exam, on my test, you'll have to use that formula. I don't think you're allowed, I'll have to look into that, if you're allowed to use programmable calculators. You can use calculators. I don't know about,
I think
you did?
it up that one time.
Yeah, but don't they have to be cleared before you use them?
I don't think so. Mine's built in, so.
I don't know. Yeah, it's true. Yours is built in. Well, either way, my guess is because it's an exam where they're trying, you only have 20 minutes to do this section or whatever. It's going to be one that either works out to be a perfect square, or it's going to be one that you don't have to do that for. If it's a perfect square, we've seen those before, right? And you know how to do those. All right. Anyway, either way, x comes out to be for this guy 0.325. That was good. Atmospheres. Now, this would be nice if the question asked, and it could have asked. Let's just change this question right now. What would the pressure of SbCl5 be at equilibrium? And the answer would be 0.325 that's what x is, right? So the 0.396 minus 0.325, or what? 0.071. And that will be your answer, 0.071 atmospheres. Okay? But the question didn't ask me for atmospheres. What did it ask me for?
Moles.
Moles. What will I have to use again?
The ideal password.
Yeah. PV equals nRT. I'll solve for moles. Which one's moles in there? N. So N equals PV over RT, which equals my pressure, which is, don't use this number, that's only X. The pressure is actually 0.071 right now. 0.071 atmospheres times the volume, which is 5.0 liters, over
721 Kelvin.
0.0821 liter atmosphere Kelvin and 721 Kelvin. So you get 0.0060.
Molar.
Moles, not molar.
Mole.
Hey, good. Another question I could have asked. What if I asked, what's the molarity of SbCl5? You could divide that by 5, or you could have just solved the equation as what? Instead of solving for N, what could you have solved for? Think about it. PV was nRT, right?
Yeah, so
I could have solved for N over V, couldn't I have? Right? If I wanted to. If I wanted to. I don't.
I would never do that, but I need it for her.
Hey, how about that for perfect timing? We're just out of time. I'll give you the homework. We're going to work on the homework tomorrow in class.